Hello all, this is Mr. G and this is our warm-up for today's lesson. So pause the video right here, give these three problems a shot, and come back when you think you have an answer. We're going over it in 3, 2, 1, let's go. So the directions say to graph each linear function. So number 1 and number 2 are actually sort of special cases because we only see one variable. Normally, at least when I think of a linear function, I think of the formula y equals mx plus b. Hopefully that's what you thought of as well. But we don't actually need that formula for number 1 and number 2 because they have only one variable, which means they're special cases. When we see only one variable in a linear function, that means it's either a horizontal line or a vertical line. So the way I do this is I say, okay, number 1 is y equals 3. So on the y-axis, which is the vertical axis, I go to 3, 1, 2, 3. And then the key, at least for me, for special case lines, vertical or horizontal lines, is I cut across the axis. That's so important. I'm going to repeat that. I cut across the axis we're on. So we're on the y-axis right here. So to cut across it, it's not going to be a vertical line. We have to cut horizontally across the y-axis. That was kind of ugly. Let's try that again. That's a little better. And there we are. That's our line, y equals 3. Let's move on to number 2. Number 2 is x equals -4. Again, we see there's only one variable, which means it's a special case. It's either vertical or horizontal. So let's go to x equals -4. So there's the x and y axis, or go to -4 on the x axis, I should say. So 1, 2, 3, 4 to the left, put a point right there. And then again, the key is we cut across the axis. This time we're on the x axis, so we have to cut vertically to cut across that axis. And we get that vertical line for the line x equals -4. All right, just one more to go in the warm-up. Number 3, it says graph 4x minus y equals 6. Now here we have to use y equals mx plus b. Now, quick review in case any of us need a review from Algebra 1. Y equals mx plus b is sort of our bread and butter for graphing linear functions. The m is the slope, and hopefully as soon as I said slope, you thought, oh, that's just rise over run. And for b, that is the y-intercept. That's essentially a point where our line crosses the y-axis. Now, before we can even think about using y equals mx plus b, we have to make sure that y is by itself. If there's anything else over there with y, it's not yet in slope-intercept form. It's not yet in y equals mx plus b form, because that's what we call it. I'm not even sure if I said that before, so let me repeat that. Y equals mx plus b is slope-intercept form because it gives us the slope and the y-intercept. Real creative, right? Yeah. All right, so let's jump into this problem. Let me rewrite this down here. So it's 4x minus y equals 6. Remember, the first thing we need to do is get y by itself. So to do that, we have to get rid of the 4x by subtracting it from both sides. So that becomes -y equals, you could put 6 minus 4x, but I'm going to put -4x plus 6, just so it already starts to look a little bit more like y equals mx plus b. And then y is not yet by itself. We're going to divide by -1, divide all the terms by -1. Need a little bit more space so my face is out of the way. This becomes y equals +4x minus 6. So there we go. I always write down the slope, I always write down the y-intercept, the b value first, because that's our starting point. So that's -6. So we go back to our graph, go down 1, 2, 3, 4, 5, 6 on the y-axis. There we go. Now the slope, the m value, is 4, but I'm going to write this as 4 over 1 because remember, this is our rise over run. So that means from any point on this graph, to create this line, we just go up 4 and to the right 1, since they're both positive. So from our y-intercept, we're going to go up 1, 2, 3, 4, and over 1 to get our next point. And the nice thing about the slope is that we can just keep on doing that. I'm going to go up 1, 2, 3, 4 over 1, 1, 2, 3, 4, right 1, 1, 2, 3, 4, right 1. Now, if we wanted to get a point on the other side, we would just reverse it. Instead of going up 4 and right 1, we would go down 4 and left 1. So that's what I'm going to do. 1, 2, 3, 4 down and 1 left. And then even if my line's not perfectly straight, which of course it's not going to be because I can't draw that well, I've got all those points in there because I repeated the slope over and over again. That's what makes a line a line. The fact that you can take the same slope and repeat it over and over and over again. That's what creates the line. Okay, that's our warm-up. Let's take a look at our objective. Today's date is September 13th. We're starting Chapter 3 with Chapter 3, Section 1, Chapter 3 is called Linear Systems, and after today we should be able to classify two variable systems using their graphs. Classify two variable systems using their graphs. So let's jump right in with sort of an important question. What is a system? A system is something that we should remember hearing about in Algebra 1. Anytime we have a system, that just means we have a group of two or more equations. Two or more. Might be more, and in fact, it will be more eventually. And then the next question, which I can sort of understand someone saying is, all right, well, when do we need these things in math? Like, when is one equation not enough? When do we need more than one equation? Two or more, I should say. Let's take a look at a few examples, a few questions to figure this out. When do we need these things? So the question is, can we find a numerical solution, essentially a number answer, to the equation? Why or why not? So let's take a look here. It says 3x plus 5 equals 17. Can we find a number answer? Sure. Yeah, we can just take away 5 from both sides, and we end up with 3x equals 12. Divide by 3, and we get x equals 4. So yeah, that's our numerical answer. Yeah, we could find it, no problem. Let's take a look at the next one. Here, same question, but now the equation is 12n minus 8 equals 3n plus 2. Could we find a number answer? Well, yeah, of course. I mean, we've got to combine like terms here. We can take away 3n from both sides. And tell you what, let's add 8 on both sides, because that'll cancel that out and there as well, make this a little quicker. 12n minus 3n becomes 9n equals 8 plus 2 is 10. Oh, that's kind of an ugly number, 10 divided by 9, but that's still an answer. We still found a number answer there. So yeah, we can find a number answer. How about this one? Same question, can we find a numerical solution to the equation why or why not? But here it's 2x minus 5y equals 11. Well, we might think, well, it's just an equation. Sure, we can probably find a number answer. Let's start solving. So, okay, we add 5y on both sides to try and get our variable by itself, but then it's like, okay, wait a minute. Now we've got variables on both sides. That's a step in the wrong direction. So that can't be it. That can't be it. So then it's like, oh, maybe we need to combine them like we did in the second one. Here we combine like terms. We combine the 12n and the 3n. Maybe we can do that here. But that doesn't help us because we have a 2x and a negative 5y. We cannot combine them because they're not like terms. So the answer here is no. We cannot find a numerical solution to this equation because we have more than one variable. We have more than one variable. So really, the answer to this question, for this one, yes, we could find a numerical solution because there was only one variable. This one, yeah, we could find a numerical solution because it may look like there's two variables, but they're the same variable. So that's really just one variable. But for this last one, we cannot find a solution if we only have one equation. And this really leads us into this question of, when do we need a system? When do we need more than one equation? The answer is when there's more than one variable. If we have more than one variable. And another thing to really take our understanding of this to the next level, the number of variables we're looking for has to match the number of equations we need. Maybe that's not the best way to say that. Let me say that the opposite way. The number of equations we need needs to match the number of variables we're looking for. So essentially, if we have one variable, one equation will do it. If we have two variables we're trying to find, then we need two equations. If we have, three variables we're looking to solve for, then we need three equations. So the number of equations and the number of variables must match for the system to be solvable. All right. Now a little bit of function rule review here. This is something you should remember from Algebra 1, but we're going to need it in today's lesson. So let's bring it back to the front of our brains. So how do we read this? So think about that for a second if you need to. How do we read that? Well, if you said f parentheses x or f times x, unfortunately that's incorrect. We read this as f of x. F of x. Now, some of you might be thinking, wait a minute, doesn't of usually mean multiplication? This is one of the exceptions to that rule. This does not mean multiplication. It's not f times x, it's f of x. And similarly on the next one, this is g of x. Okay, not g times x, not g parentheses x, g of x. Now this question right here is really important. What do the f and g represent? The f and the g represent functions. They represent the function that we're dealing with. Okay? F and g are not variables. We're never going to solve for f or solve for g. That doesn't make any sense because they're not variables. They represent which function we're dealing with. Are we dealing with the function called the f function, or are we dealing with g? Okay, f of x or g of x. The f and the g represent different functions. All right, so keep that in mind as we move forward. Okay, that was a whole bunch of setup. Let's actually get into some examples here. So example 1, it says locate the solution or solutions to the system on the graph. So the system right here is y equals f of x and y equals g of x. Basically that means, okay, we've got this f of x function and this g of x function. Now this is something you should remember from Algebra 1. The solution is always where they intersect. So the solution is the intersection. That's so important. I'm going to write that down. The solution to a system on a graph is the intersection, or intersections if there is more than one. The solution is the intersection. And if we look here, this point right there is where f of x and g of x cross. That point is in both functions, which means it's a solution to both equations, which means it's a solution to the entire system. Because a solution to a system has to work for every single equation that's in that system. And this is the only point on this graph, that point right here. That's the only point that is on f of x and g of x. So that means it's the solution. So there was one solution here. Now let's take a look at example 2. Same directions, just a different graph. Here it's y equals f of x and y equals h of x, but the h doesn't really throw anything off. It's the same thing as f and g. Well, remember the solution is the intersection, so we see one solution right there and another solution right here. Here there are two solutions. There are 2 points on this graph that work for both of these functions. So this system has 2 equations. So far, so good. Let's take a look at number 3. Same question, locate the solution or solutions to the system on the graph. Here we've got g of x and h of x, and I don't see any intersection, which means there's no solution. So there's no solution here. Because the lines, the linear functions, never cross. So there's no point on this graph that will work for g of x and for h of x, because g and h never cross. They never touch. So there's no solution. Now, example 4. It's the same question, locate the solutions to the system on the graph. And here it can be kind of tough to see. So we've got f of x, which is the black line right there. And we've got g of x, which is the blue line, also right there. So the question is, okay, if the solution is the intersection, where is that on this graph? And basically the answer is there's all sorts of solutions here. Okay, we've got a solution here, we've got a solution here, here, even in between there. Every single point we can draw on these lines is a solution because the lines are right on top of each other. They're directly on top of each other. So my question to you, think about this, would be, how many solutions do we have here? I mean, back here we had one solution, then we had 2, and none. How many solutions are we looking at here? The answer is there are infinitely many solutions here. Infinitely many solutions. Now that doesn't mean that any point we pick is a solution. Like this point, that's not a solution because it's not on the line. But there are infinitely many solutions because remember, these arrows mean the lines keep on going forever in those directions. So no matter how many points we pick, there's always going to be more possible solutions to this system. So now what we're going to do is we're going to take what we just learned here and sort of looking at these graphs and sort of put some vocab behind it. So now we're going to talk about how we can classify linear systems. So there's 3 main types of linear systems. There's intersecting lines, there's coinciding lines, and there are parallel lines. So we're going to take this one column at a time. So with intersecting lines, that means there's one solution. They only cross once. So here the solution would be right there. Now, we call this type of system consistent. Consistent means that there is a solution, one or more solutions. And since there's one solution, we call it an independent system. An independent system has one solution. The way I remember that is like, okay, an independent person, they're out there, individual, on their own, one. It's all about number one, you could sort of think. So that's an independent system. That's how I remember it. Kind of stupid, I realize. Now, this is important right here. What's in italics there is how we can sort of figure out what type of system we're looking at, even if we don't have a graph. So if we have two linear equations in one linear system, and the two equations have different m values, their slopes are different, then automatically they will be an independent system, a system with one solution. All right, so keep that in mind. We don't even need to look at the y-intercept. We don't care about b. As soon as the slopes are different, one solution, which means it's independent. Now let's move on to coinciding lines, the one right in the middle. So this is when the two lines, and again, it's kind of tough to draw this, but the two lines are right on top of each other, right on top of each other. Essentially, they're the exact same line. So this is when there are infinitely many solutions. And again, there still are solutions, so it's still consistent. But now, since there's more than one, we call it a dependent system. The way I remember that when they're right on top of each other, it's a dependent system. It's kind of silly, but I don't know if you've ever seen this when like two people are in a relationship and they're just always with each other, always talking, always doing this, always doing that. And it's like almost to an unhealthy level. Sometimes people look at that relationship, man, that's a codependent relationship there, where you're with each other too much. Okay, well, we're dependent right there. These two lines, they're just with each other too much. They're always on top of each other. It's dependent. It's a dependent system. Again, kind of stupid, but it works for me. Now, this is probably the most important part. This is how we tell, without even looking at a graph, just looking at two equations, if they will create a dependent system. This is how. They have to have the same slope and the same y-intercept, which sort of makes sense because they need to be the exact same line. All right. Now, last but not least, we're going to move on to the parallel lines. Now, I'm going to have to slide down a little bit to get my face out of the way. There we go. Let's go up a little bit so we can read. Then we'll scroll down as we need to. So parallel lines, that's when there's no solutions, no solution at all, because they're never crossing. They're never crossing. Now, since there are no solutions, we call this an inconsistent system. It's not consistent. It's inconsistent. There's no solution at all, which makes it different than intersecting and coinciding lines. Now, how we tell just by looking at two equations that it's inconsistent without even needing a graph, we just say, okay, are the slopes the same? And the y-intercepts have to be different. So same slope, different y-intercept, which sort of makes sense because they have to be going parallel, which means they both have to be going the same direction, but we don't want them right on top of each other. Otherwise, it would be dependent. So, okay, they're both going the same direction, but maybe one's a little higher up or a little lower down, and that's exactly what a different y-intercept would do. All right, so that was a whole bunch of information. Let's apply that. Oh, right. This question. I can understand some students looking at this and saying, wait a minute. Didn't we see a system with two solutions? Now we're talking about one, infinitely many, or no solutions. Didn't we miss something? If we look back, is this a linear system? No, it's not a linear system because h of x is a parabola. It's not a line. So a linear system, a system of two lines, will only ever have one, infinitely many, or no solutions. So just keep that in mind, ladies and gentlemen. All right, let's jump to example 5. So without graphing, classify the system as independent, dependent, or inconsistent. So really this all comes down to the slope and the y-intercept. So let's color code this. I'll do this one in blue and this one in green. So the blue slope, that's 2, and the blue y-intercept, the blue b, is 5. All right, that one was pretty easy because y was already by itself. But unfortunately, in the green, y is not by itself. So we got a little work to do here. So I'm going to move this over. 4y equals 2x plus 6. And then to get y by itself, we divide every term we see by 4. Hopefully we remember this from Algebra 1, just getting y by itself. So then that becomes y equals 1/2 x plus 3/2. 3 over 2. All right. So the slope here is 1/2. And right now, if you're thinking ahead, you think, oh, we don't even need b. We're done. Because if we look at our two slopes, the two slopes are different. They're not the same slope. And if the slopes are different, that means they're automatically going to intersect once, giving us one solution, which means it's an independent system. Independent system. So that's the answer. That's all the directions we're asking for, right? Yep, we classified the system. We don't have to solve it. We are finished. It's an independent system. All right, moving right along. Example 6. Without graphing, classify the system as independent, dependent, or inconsistent. Same directions. Again, I'm going to color code this. Let's do this one in blue, this one in green. Here we've got to get y by itself in both of them, so it's going to be a little bit annoying, but that's okay. That's okay. So let's do the blue over here. So it's 3x minus 2y equals 8. Let's move the x first. So let's subtract 3x from both sides. Scroll down a little bit. So that becomes negative 2y equals negative 3x plus 8. Let's divide everything by negative 2. And that comes out to y equals 3 over 2x minus 4. And now we're ready for our slope and y-intercept. Come on, scroll down. So our slope is 3 over 2. And the b is negative 4. Good, good, good. Okay. Now we need to do the same thing for the green. So let's copy the green over here. Now while I'm copying this, ladies and gentlemen, if you're good enough to do some of these steps in your head, that's a good thing. I'm just showing all my work so I don't lose anyone who's watching the video. If you can skip some steps, by all means, more power to you. Did I copy that correct? I did. Okay, so here, all we have to do is add 3 over 2x. That's not too bad. To both sides. Let's see. So we end up with y equals 3 over 2x plus 4. Now we're going to look at our slope and our y-intercept. The slope is 3 over 2. Y-intercept is 4. Now let's compare. All right, the slopes were the same. I forgot to check that if they were different. So they're the slopes are the same, which means it's either parallel or they're either right on top of each other coinciding. The y-intercepts are different though. So we've got the same slope and different y-intercepts, which means they're parallel. They're going the same direction, but they're not on top of each other. One is higher than the other. So that means no solutions, which means it is inconsistent. Inconsistent. I think I'm spelling that right. If not, just don't tell your English teacher. Inconsistent. Same slope, different y-intercept. All right. That was a lot of me talking. Tell you what. Pause the video right here. Try these two on your own. So example 7, there's 2 parts. There's one system, so this system right here, and this system right here. I want you to try these two on your own. So classify the first one as independent, dependent, or inconsistent, and classify the second one as independent, dependent, or inconsistent. We're going over answers in 3, 2, 1. Let's roll. So let me see. For the first one, let's color code it again, blue and green. So the blue is x plus y equals 4. There we just need to subtract x to get y by itself. So we get y equals negative x plus 4. That makes our slope negative 1 and our y-intercept b of 4. Okay. Now we're going to do the same thing with the green. So here it's negative 3y equals 3x minus 12. Got to get y by itself, so we divide every term we see by this negative 3 we have to cancel out. And there it goes. And we get y equals, that becomes negative x plus 4, giving us a slope of negative 1 and a y-intercept of 4. And look at that. We've got the exact same slope and the exact same y-intercept, which essentially means these are the exact same thing, which means this is a dependent system. This system is dependent. 2 coinciding lines. Which means there's infinitely many solutions. Let me go back up and drag this one down so we have a little bit more space to work. This one was a little different. A little bit different because here we only have one variable. We've got x equals 5 and x equals 1. So we don't really, I don't want to say this, we can't really get y by itself because there is no y. So we can't really compare the slope and the y-intercept. I guess technically we could compare the slopes, but I don't want to do that. I just want to sort of think about this. Well, x equals 5 and x equals 1. What kind of lines are they going to give us? Well, there's only one variable, so that means it's either horizontal or vertical. And like I said in the warm-up, my trick is we always cut across the axis we're on. So if it's x equals 5, okay, that means we're on the x-axis. So that means to cut across it, we need a vertical line. So this is going to be 2 vertical lines. So essentially that means the 2 lines are going to be parallel. They're never going to touch. So if they're parallel, there's no solution. That means it is inconsistent. Inconsistent. And we are finished. And that's our lesson for today. At this point, you should be all ready for your homework, which is page 139, numbers 17 through 20. It's only 4 problems, and all you have to do for these problems is basically what we did in our examples. They're going to give you a system, and without graphing it, you have to say, okay, is it independent? Is it inconsistent? Or is it dependent? I said that in a weird order, but whatever. That's all you have to do. classify the linear systems. If you have any questions, by all means reach out. Otherwise, enjoy the rest of your day.